Hello everyone, today I'm gonna talk to you about linear regression analysis. For my students, I'm gonna just very quickly go over what we covered in class, and hopefully you will be able to have a more connected it's going to be one recording better than multiple recordings, and you connect the dots. I'm going to connect all the dots that we covered in class in one recording only. So for today, I'm going to power through it. You need to use your height and age and height Excel sheet that I sent to you in class, or I shared with you in class, as well as the regression notes that I shared with you over Moodle. All right, we're talking about a linear regression analysis. With linear regression analysis, I'm going to start with simple linear regression. With simple linear regression, we're talking about two variables only. The first variable would be a variable that will be plotted on the y-axis. It's the variable that we are intending to study, and the other variable will be plotted on the x-axis, and this is the variable that will help us explain the variation of the value of the other variable, or this variable will help us to predict the value of the other variable. Let's take the example of toddlers over here. I'm going to give you another example as well. The first example here that we have is as toddlers age. So first for example, this is the data range here from 18 months to 29 months. As toddlers age, we expect them to get taller. So as their age in months increases, we expect their height to increase as well. Right? So basically, for this example, we could easily understand that height is the outcome or the response of aging. So as they are aging, as their age increases, the toddler's body responses by getting taller. This is why height is the y on the y-axis. This is the target, we call it, or the outcome in the model, or in this study. And we use the word, also the label target, when we're talking about, for example, programming Python and so forth. We use it as a target, or we label it as a target. But for our marketing modeling purposes, we call it the dependent variable, because its value depends on the age. The height will not increase on its own. You don't give too much water and then the kid after 2 hours will get taller. Actually, you have to wait until they age, so that they get taller. Of course, you give them water and food and everything to get taller. But what I meant is this variable will be dependent on the value of this variable. This variable, on the other hand, will be the independent variable. All right. There are other labels as well. So this could be the target. This could be the dependent. Also, this variable could be the response, because it responses to the age. So it could be the response variable. This could be the independent variable. This could be also the explanatory variable. So this, another label for it is explanatory variable, because it tries to explain the other variable, the dependent variable. So explanatory variable. It also could be the predictor, because over here we're trying to predict the height of the child, the height of the toddler as they age in months. So this could be the predictor, the explanatory, and the independent. Let's talk about another example, guys. Another example I would like to discuss with you is answering the researcher question: how does phone use before bedtime affect sleep? What is the target here? What is your dependent variable? What is your response variable? Your sleep is affected by the use of mobile phones before going to bed. So sleep in this example will be the dependent variable. How could you measure sleep, guys? There are 2 ways or 3 ways or multiple ways that you could measure sleep. I would like to give an example of 2. The first one is measuring sleep by the number of hours that you slept. And in corresponding to that, you will measure here, as the question indicates, the question is, what does phone use? So here's phone use, right? The phone use is the independent variable. So basically over here, what you're trying to do is measure both the phone use and the sleep. Phone use basically could be measured by the number of minutes. I hope in minutes, not in hours. So let's say that number of minutes the phone use. And over here, sleep will be measured by the number of hours. In this case, the number of hours, the type of this variable is numerical. Let me just say it's a numerical variable. It could range from 0 all the way to, let's say, 10 hours, not more than 10 hours asleep. For adults, it's recommended that it's 8 hours. For some adults like myself, I would be very lucky if I get 6 hours of sleep. So in any case, this is the number of hours. It's a numerical. It is continuous within this range. So we also say it is a continuous variable type or continuous type. Another way that you can, in fact, study the sleep quality or the sleep here is by sleep quality. You could basically ask the individual, the subject, either they had very good sleep or satisfied with their sleep, or they had very bad sleep, that they are not satisfied with that sleep. So the response variable over here, or the dependent variable, will be of the type of either, if it's good, we can code it as 1. If it's bad, we code it as 0. In this case, we call this binary, isn't it? It's binary. It's 1 and 0. Only 1 and 0. So it ranges only between 1 and 0. It's like a categorical. So it's a binary variable. It's a categorical variable. In this case, guys, we need to understand one little thing about regression. If the variable is collected in a continuous numerical type as indicated over here, the number of hours of sleep, then linear regression is the right technique to be used. If the variable over here, sleep quality, will be measured in terms of binary, 1 or 0, then this will be the best technique to predict this value, either predicting it as 1 or as 0. For this, we will use what we call it logistic regression. So this is the first step toward understanding when to use linear regression. The dependent variable over here, lovely people, this one, the dependent variable, the height, should be of a numerical order. All right, the height should be of a numerical order. And in this case, we can study it, or we could investigate whether linear regression is the right model to use to predict its values. All right, let's talk about here. The first thing toward investigating simple linear regression is basically plotting the height versus age. Yeah, over here. Plotting the height versus age by using the plotter's the scatter plot. So basically you just go highlight the height and go to insert and then go to scatter plot over here, scatter. Once you do that, as you can see here, what you need to do is you can actually format it. It's up to you. So if you format it, if you want to like chart design, you want to here you can mimic the same chart as before, and over here you right click and you add a trend line. If you add a trend line, choose the linear line and also display equation on chart. And let's do display r squared as well. For simple regression, it might be helpful. So over here we have the chart over here has plotted a trend line, a linear line. This linear line is considered to be the best linear line that we could get that is closest to all the data points. I will talk a little bit about it right now. All right, so now this is what we call it, the linear model. The linear model is this linear line. So this is what we call it, the linear model for, I'm sorry for my handwriting, I don't think you can read this, so let me just be a bit patient. This is the linear model. And this linear model is basically holds the values of the predicted values. These are the predicted values. Yeah. While these points over here, these little points over here, the points here are the actual data. So these are the actual data points, and this linear model this line constitute of the predicted values. All right, good. Now the question, how did Excel come up with this line? Very good question. Excel could have, or you, if I gave you this scatter plot and I asked you to draw the best line, you could have probably drew the line a little bit slightly different. You could have probably drew it like that, a little bit closer but different, or like this, or like whatever way. Yeah, you got the point. So there may be other ways of drawing the line, but which line is the best line? This is the question. So there are, in principle, you could draw multiple lines, right? I could draw the line that I thought is the best fit, the best line, and you will have your own theory of what, or your eyes could see the best line to be tilted, or it's a sloped, or its steepness in a different way. So basically, there is an algorithm that is used to determine the best line. Yeah, and this is called the ordinary least square. The ordinary least square. And of course, here in the here's I have multiple examples for you guys, and over here I have the definitions and examples of the dependent and independent variables, and over here I'm starting to explain to you this example in particular, the age and height and what you need to do. So basically I'm talking about how do we specify this linear line. If we have multiple data points around it, how do we know that this is the best line? So basically, we use what we call it, let me just go ahead over here, what we call it the ordinary least square error, or least squared error. And this is a very simple idea. The idea is, if this is the actual data point, the point in red, in green, and this is the predicted value, the corresponding predicted value that we found by dropping here a vertical line on, as you can see here, we dropped a vertical line all the way onto the linear model, or the linear line over here. So this is the corresponding predicted value on the line. Yeah. Okay, so basically what happens is this distance over here is what we call it an error. Why do we call it an error? Because the optimal scenario, the best scenario, is we have the lines lining up like that. Yeah, this is the best scenario. For example, this is X and this is Y, and the lines are lining up like that, and we just so lucky that actually the predicted values are equal to we find out that the predicted values could be exactly equal to the actual values. This means that my prediction accuracy is 100%. What are the odds? This is, of course, a very hypothetical example that is not, it cannot really happen. We have different problems with overfitting, and this is, I will talk about it later. But for now, we're just talking about almost all the time there will be a little error. The accuracy should be, we should aspire to have a very high accuracy, and very high accuracy is basically a line that is as close as possible to all these data points. Yeah, and for this purpose we use ordinary least squared error, so that we can find the line among all the possibilities that I just talked about. We can draw a line here, here, there, and there, which is the best fitted line. So we need to get the line that has the least distance between the actual and the predicted, meaning the least amount of error. For this purpose, there is an algorithm, an established algorithm. Now, students, this algorithm depends on the distance between the actual and the predicted value. As you can see over here, for example, these distances are positive distances or negative distances. We'll see. The error, in fact, depending on how you understand, the error, in fact, is the actual, let's say it's A, denoted by A, minus the predicted value. So if the actual value is above the predicted value, this means the actual value is over or is greater than the predicted value, right? This is the actual value on the y-axis, right? And this is the predicted value. right? So the actual value over here is greater than the predicted value. So this error sign will be positive. On the other hand, if we take a look at this point, this is the actual value, all right? And the corresponding predicted value is somewhere here. Somewhere here. So the predicted value is higher than the actual value. So in this case, for these points below the line, for this point below the line, for this point, here's the error. For this point below the line, the error will be A minus B, where B is greater than A. Here, where A is greater than P, where P, oh, okay, sorry, it keeps on, okay. So error when A is greater than P, and here the error when P is greater than A, what happens is the sign will be negative, okay? So if you want to get the best fitted line, basically you want these points to be as close as possible to the line, right? So you need the sum of errors to be as small as possible. So basically we're talking about sigma error. Let's say the error is epsilon here. So it is sigma I error. Let me use E then. Let's say that this is error I. Basically, I is 1, 2, 3, 4, 5, 6, and so on. So this is the measure that we would like to find out the sigma of the error, the sum of errors over here, the sum of errors over here. The sum of errors is basically we want to minimize it. So we need to minimize it. As we covered in class in different models, it's a minimization problem. So minimization problem for what? Minimization problem to find the line, the best line. How do we find the best line? The best line is basically for linear regression. We're talking about here, I need to fix this by the way. Linear regression in general is actually taking the form, some students know it as y is axi plus b. B is the intercept and a is the slope. Yeah, so over here, if we take a look at this picture, the slope is delta y over delta x. So y is equal to the y-intercept here could be b. So it could be, and the slope could be a. So a is equal delta y over delta x. So basically, you're talking about ax plus b. B being the intercept and a being the slope. So basically you want to get the least errors. So if we have here E and here's AI. Actually, this is now multiple regression. We could also talk about multiple regression by adding I and I over here. So we have multiple parameters here corresponding or attached to the X, and only one intercept at all times, and multiple errors based on the Over here, we're talking about the parameters. So the parameters here, y is equal ax plus b for simple regression. Of course, we have multiple points. So we can put ai plus the slope here is one slope, and the intercept is one intercept. So we need to find these parameters, the slope and the intercept, where we have only one slope and one intercept, but along multiple points of y and x, all right? So how do we find these? In such a way that sigma ei corresponds to each point, of course. Sigma ei, the sum of errors, is minimized. So we trying to minimize the sum of errors so that we can find A, so we can find B. All right, how do we do that? There is an algorithm called the ordinary least square, and over here, this model is based on this notation, and this notation here is yi is equal to, this is supposed to be alpha, this is not the right one, it's supposed to look like that, alpha beta I here, xi plus error I. This is for multiple regression. So basically, if it's a single regression model, beta over here could mean the slope, and in this case there's only one slope, there's only one intercept, right? But if it's multiple regression analysis, then we will have not one x, we will have x, x2, x3, and so forth. So in this case, we will have also multiple different coefficients for each x. So this will be beta 1, beta 2, beta 3. I'm going to talk about this in due time. But let's talk about this model being a simple regression analysis. Have a beta here, 1 beta, or this is a xi plus this is the error. And over here is b is the intercept. Okay, so it's the same. So in this case, we just need to minimize the errors. But if you can see here, if you see here, take a look, it is actually the error term is actually squared. Why is that? This is because the distance over here, as I explained earlier, the distance of these errors that has the positive sign will be canceled out by those with the negative sign. Yeah. When we minimize, of course, the sum of errors. This means that we're going to cancel out some of these errors. So the sum of errors here is supposed to be a representation of the distance here of the point and the predicted line. But it's no longer a very precise prediction because of the difference in signs. One will cancel out the other. We might get half of the distance, the real distance, just because this distance is negative, this distance is positive, they cancel out each other. If they are equal to each other, then this will be a sum of 0. So we are missing out on these errors. Yeah. So for the purpose of avoiding the signs, we're actually going to get squared. Now, some of my students ask me, why don't we get the absolute value and that's it? Why? Because as a mathematician, if you want to propose an algorithm, you need to give a proof. Yeah, so you get a theorem and you get a proof. So for you to prove it, it is easier to prove it, and it was possible to be proved with the squared. So I could go over the proof of this theorem or this algorithm, but this is beyond our scope because this is not a math or statistics, it's marketing modeling course. If it was a math or statistics course, I would be more than happy to show you how to do this. But just for now, for those students who are a little bit curious why we are using the squared errors and not the absolute errors, it's because of basically merely it's because of the fact that we could prove this theorem easily, that this minimization over here will be equal to a minimization of this and all that. We were able to find out that this will get the best fitted line, but over here it was very difficult to find out the proof, and this is why. All right, so this is about the ordinary least square. Ordinary least square basically minimizes the error so that we can find alpha, which is the error. Alpha is the intercept, and beta here is the slope or the coefficient of x. The coefficient, it's the weight. So these, we basically say this technique gives us the best linear unbiased estimators, blue. So blue corresponds to the best linear unbiased estimators. All right, so now that we talked about the algorithm over here, how do we find the best fitted line? We want to prove if this line is good enough. If the data, remember, the data points, the actual data comes before the line. So maybe the data looks like that. And the best line is like this, or actually better example is something like this, like the data looks like that. And we can still draw a line. However, this data could be better fitted with a different model. Instead of linear, line, it could be better fitted by quadratic equation. So in principle, the actual points are actually comes before the linear line, or comes before the model. So you are fitting a model on the points. That doesn't mean that this is the only best model that can actually predict the values. So we need to study something that is called the goodness of fit. Let's go over to the goodness of fit. What is a goodness of fit? A goodness of fit is how good does the model fits the data, how close they are to the linear line in terms of linear regression, and how well and how precise that model in fact predicts the future set of observations. For this purpose, we use two different measures. The first one is R-squared. However, this is multiple R-squared. For linear regression, if it's simple linear regression, I don't mind the R-squared. The R-squared is basically a measure that tells you how all the independent variables in the model, how much they could explain the variations in the value of the dependent variable. Okay, so now we understand that this R-squared is actually telling us how much variations this model could be used to explain the values of the dependent variable. I need to note that for multiple regression analysis, when we're having more than one variable to predict the height, for example, we have age, we might have also the nutritions, or maybe a certain medication for certain toddlers, and see if it affects their height positively or negatively, and so forth. So there are multiple x's here, multiple variables here on the x-axis. We have x1, x2, x3, and so forth. In this case, for multiple regression analysis, using R-squared is a big disaster, I'm telling you. You don't use the multiple R-squared, you use what we call it the adjusted R-squared. Why? Because as the complexity of the model increases by adding more variables, this is something that we actually as scholars, or you also as a student now, should favor, because this means that the model is more robust. Yeah, it has more variables to predict the dependent variable. So this is a more complex, more robust variable. Assumption, this is the general assumption to be, if all the variables are useful in predicting the dependent variable. However, there is a problem with R-squared. There are multiple problems with R-squared, but one of the most important problems with R-squared is R-squared value, multiple R-squared value increases as we increase the number of variables, independent variables in the model. Even if the independent variable that we are adding is not necessarily beneficial in the model. For example, if we add something like here, the number of siblings, do you think the number of siblings has an effect on the height of the sibling? So even if we add this variable, and I'm going to show you in a bit how we adding this extra variable that is, we know that is not beneficial, is still R-squared value will actually increase, indicating that the model is better explaining the variation of the dependent variable, or better explaining the dependent variable, or better predicting, or better fit, basically. And this is a problem. For this purpose, scholars adjusted the value of R-squared with an adjusted R-squared measure. An adjusted R-squared measure is equal to this formula, as you can see. N is basically here is the number of observations, or the data points that we are collecting. So for example, here the number of observations is 1, 2, 3 is here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points. So this is observations. Now, how about here, K? K is the number of independent variables. For our first example with height and weight, our independent variable here is only 1, so K will be 1. So basically, this is how we compute the adjusted R-squared, and this is what you need to look at to explain how the model in totality explains the variations in the dependent variable. All right, now another thing that we're going to talk about is the difference between R-squared and R. R-squared comes from R. R is actually Pearson correlation. R is a Pearson coefficient, or a Pearson correlation. It tells us R ranges between -1 and 1. -1 indicates a negative relationship. Basically means over here, as you can see, r is minus or negative 0.90. This means that as we shift forward or we move forward 1 unit here on the x-axis on the independent variable, or as the independent variable increases by 1 unit along the x-axis, as you can see, as it increases here, the value of the y over here decreases. So over here, the value of the y was 40. As we're shifting toward here, the right, to increase 1 unit forward, the value is actually decreasing here of the y-axis, and vice versa. Actually, not vice versa. I'm sorry. This is usually we shift from. We always, our origin is the 0 here, and we are moving or shifting 1 point forward on the x-axis for linear regression. Okay. So as this increases, in fact, this decreases. So this is what the negative sign means. All right, over here, how about the positive sign? As you can see, as the x increases, also the y increases. So in this case, as you can see, this is a positive correlation. Over here, positive linear correlation. Over here, the r over here is 0, is very low. This means that these data points are not linear. The model shouldn't be linear. The correlation is not linear. But is there a correlation? Yes, there is a correlation, and it could be modeled with a quadratic equation, with a quadratic model. However, a linear model, this is not a linear relationship, but there is different correlation. So this is what the R Pearson coefficient or Pearson correlation means. All right. Now for adjusted R squared, or let's talk about R squared. For R squared, it ranges from 0 to 1. Adjusted R squared, in principle, it should range from 0 to 1, but sometimes it could be negative. In this case, negative indicates a problem with adjusted. Let me write the word adjusted here. The negative, and this is more advanced situations. The negative means that the proportion of the n, do you see the n here? In the adjusted R square, we have n and k. K is the number of independent variable, means that the observations, the number of observations is not sufficient. Is not means it is not enough or proportionate to the number of independent variables. For example, you can't have 5 independent variables and 5 observations. This means what? It's very little. You got my point. So you have 1 independent variable and 10 observations. It's not the same when you have 10 independent variables and the same number of observations, 10 observations. As the number of explanatory variables or independent variables increases, so as the number of data you need to collect, all right? So data points you need to collect. So in this case, adjusted R squared could be negative. So please be aware of that. All right, so now second measure for the goodness of fit is basically the standard error. Standard error is like a standard deviation. Some of my students ask me, is a standard error is like a standard deviation? Well, if you want to understand the standard error, you could probably review your knowledge on normal distribution, where in the normal distribution, if this is the average over here, the average reading, it's in the middle, or the average is actually in the middle. So the mean, the median are equal to one another. Yeah. And then you say that the peak is here, and you say that the distance away from the mean, how you are away from the mean, indicates how precise the model is. So if you are only 1 unit here away from the mean, and this unit is the standard deviation, then this indicates that you are very much closer to the mean. Yeah. So over here is 2 units away from the mean, but still it is acceptable. And usually for you to have satisfy the normal distribution, you usually go by the rule, the 68, 95, 99.7 rule, where you say that if 68% of the data points lie in within 1 standard deviation, and if 95% of the data points here lie in within 2 standard deviation, then this will be an indication that this is a normal distribution. Same applies for the standard error. Basically, this is a 1 standard error away from 0 and 2 standard errors away. So basically, for standard errors, also you want your data to lie minimum 95% of your data to lie, or around 95% of your data to lie in within 2 standard errors. What does that mean? So this is the technical. You want your data to lie in, or 95%, about 95% of your data to lie in between 2 standard errors. What does that mean for you? This means for you as a standard error is that your data is closer to the predicted data. Predicted data is basically the mean. So basically you are very close to the your predicted points, or your actual points. Sorry, that's correct. Your data, your actual points are as close as possible to the predicted values. So the standard error, if the values or the residuals or the errors are 95% of these errors lie in within 2 standard errors, then this is also a very good measure for the precision of the line, of the linear line, or the goodness of fit. And this is here standard error. This is the equation of standard error, but in Excel we can just use STEYX, and this is a function in Excel that we could use. For adjusted R-squared, there's no function that you could use, so you could use this there's a function for R-squared, which is RSQ. Once you use this function RSQ and find the R-squared, you could use this formula to use adjusted R-squared. But nobody does that anymore. We use the analysis package or the analysis tool pack to actually get all these measures. So I hope by now you understood the difference between the adjusted R. So here I have, for my students, I have some explanations on R-squared and its differences. But I hope for now you understood the difference between R-squared and adjusted R-squared. Basically, there is an example, a very interesting example on why I always say that R-squared is not as good as the standard error for us to measure the goodness of fit. And I always say the goodness of fit, the best measure to measure the goodness of fit is actually the standard error. For example, if you take a look at the velocity, you're saying that there are 2 vehicles, let's say, and one is traveling at 20 miles per hour. The other is traveling at 90 miles per hour. And you are saying, for example, and this is the example of R-squared, for example, this is the analogy. So you're saying that R-squared is as if you are saying that I am 80% faster. 80% faster, good, but 80% faster of 20 means that it is 16 extra miles per hour, while 80% faster of a base of 90 miles per hour, a vehicle traveling at 90 miles per hour, 80% faster means 72 extra miles per that hour. So basically, R-squared is just telling us some relative measure, all right? It's just a relative measure that we don't really know what's the base here, and we don't have a quantification here. We don't know the 16, we don't know the 72 that will impress us. Oh, wow, so you are traveling 72 extra versus 16 only extra. So it tells us only that 80%. However, the absolute error, the standard error, on the other hand, is more of an absolute value rather than relative. So it's more of an absolute value rather than a relative, and it tells me exactly that you are 72 miles per hour or 60 miles per hour. So this is, I hope this example, it's an analogy. It has nothing to do with linear regression, this miles per hour example, but it hopefully gives you an understanding why this measure is more relative. It doesn't tell us the whole story. This is a more impressive measure. All right. And I hope now you understand why with this little, very simple example. All right. Having this said, I hope right now you understand how to carry on with the example. Let's take a look. Over here we have 12 different data points. Height is the y-axis, and this is the actual data. Predicted data is nothing but the using the linear model. Linear model could be found by the finding the parameters of the model. For simple regression is a slope, so you can just say slope of y and x. Over here x is age, so over here slope, and feed into the slope function the y data points and the x data points, and you find the slope. And then you have the intercept, same thing, intercepts, and here's y, you feed into it for y and x. Then for the goodness of fit, you need to find the r squared. The r squared is r skew, but actually I don't agree with that. You need to find the adjusted r squared. However, for simple regression, r squared is okay. For multiple regression, make it a habit to always use the formula that I've given to you. However, I will show you a better way. You don't have to memorize any formulas. We can use the analysis tool pack and find it out. Then for us to find the standard error, we could actually find the standard error with this very easy function instead of going over the whole formula. I've done it in both ways for fun. However, I suggest to my students that they can just use the steyx function of Excel so that they can find the standard error. Let's now talk a little bit about the error. So now that we found the slope and the intercept, the two main parameters of a simple regression analysis, we could actually find the model. Model is y is equal to this slope, 0.635, multiplied by x, the value of different x's, the age, plus 64.928, which is the intercept. What does the intercept here mean? The intercept means when x is equal 0, meaning when the baby is 0 months old, then we predict that the height is 64.928. So basically, this is the beginning value. This model is not very precise, I tell you. This model is not meant to measure newborns. This model is the range of this model. The range that this model was constructed upon starts from 18 to 29. So we can say that an 18 months old, it's just difficult to use this model. I just wanted to say that it is difficult to use this model to generalize and use it for babies from 0 to whatever. Why? Because the data range that we used to construct this model is limited, is not as representable of the population. The sample used over here ranges between 18 to 29. So it best predict the height of babies in this range, or very close around this range, but not far away to 0. Because as I told you, for 0 babies, it is from 50, maximum maybe kind of 60 or 55. I haven't seen a baby. I don't know if in the United States babies are way much bigger, but it could be about 50. I don't know really if one baby could be 60 when they are born. But in general, guys, this is a general guideline. Always in research and experimental design in general, the sample should be representable of the population. So if you are trying to use a model to predict your independent variable, make sure that you take a look at the data that this model is derived from, and you as a company, as a country, or whatever, you actually consistent. Yeah. with those measures. All right. Having this said, we use this linear model to predict the values, and then we use it to find the errors. The errors is basically nothing but the actual value given to you here minus the predicted value. Actual minus predicted is actually the model, the errors. And for you to find how good are they or how far out are they from the standard error, then you need to get this formula. This is in within one standard error. Is this point lies in within one standard error, meaning this error, the absolute value of this error is less than this. So this is what you are measuring. Is this error is less than the absolute value of this error is less than the standard error. So standard error here in positive. So we don't need to really put the ABS. ABS is the absolute value. And please make sure that you add these dollar signs so that you kind of freeze the cell. So over here, you find out your testing. Is it in within this error? Is it in within one standard error? And then find the two standard errors. Two standard error here is basically 2 multiplied by the standard error, right? So if this is over here, sorry, this is not a very good start. So if this is over here, the midpoint, and this is 1 standard error in the positive, this is 2 standard error, you need to find out if this error over here lies in within 1 standard error or in within 2 standard error. This is what we are trying to say. So if it's here less than or equal, do I have equal in there? I should have equal in there. Don't be shy. Yeah, I have equal in there. So less than or equal. So again, here's the formula. If this error is less than, absolute value of the error is less than or equal to this standard error, then give me 1, else give me 0. And then basically you just sum it up, and then find out the count. How count them. And you could also do it in one blow by saying the sum over the count, so that you can find out how much is the proportion of the data points here or the residuals that lie in within 1 standard error or 2 standard errors. Over here, I focus on the 2 standard errors in general, and I take a look if at minimum 95% or around 95% of all the residuals lie in within 2 standard errors. This is a good indication of a goodness of fit for the model. And this is the first topic for linear regression. Now let's talk about technicalities. Let's talk about this analysis tool. Oh, I'm sorry. This is, oh man, this is from my lectures, my previous lectures. So basically, I would like to show you now how to get all the things that we talked about in just a couple of clicks of a button using Excel, which is by using the analysis tool pack. So over here, we have the data points, the age and height, and we would like to find out the output of regression. So basically you need to go to data, find out if you have the data analysis. If you don't, go to file, go to options, and then all the way down, go to add-ins, all the way down, Excel add-ins, go in there and check the analysis tool pack and hit OK. So now that you have the analysis tool pack available, you need to click on it and to choose regression. So regression, okay. For the Y input is basically the dependent variable. You can select it with the label, it's okay. With the X-axis, also there is the, here's the way that you select the range. And if you select them with the labels, and this is what is recommended, you check the labels here. And residuals, I would like to see the residuals. So I don't want to compute the residuals, actual minus predicted. I want you to do it for me. And now we're going to learn a little bit about the residuals plot. And for now, I'm going to put it in a new sheet. So this is the output. Let's take a look at the output together. The output has the percent correlation. So it seems like it is a linear correlation here. R squared is not what we want to take a look at. If we have multiple regression analysis, I suggest adjusted R squared as standard error for the goodness of fit. So basically, if I ask you, comment on the goodness of fit. So you say goodness of fit, R squared or adjusted R squared, and you tell me that adjusted R squared is very high, 0.987, indicating that this model explains, or let me write it down, adjusted R squared is about 98%, or for adjusted R squared, this is what you want to see. The model is able or capable of explaining 98% of the variation of Y. I don't like this. I like my students to show me that they really understand what they're talking about. So we just say that age of toddlers in months explains 98% of the variations or the variation in their, like the toddler's height. So this means that you really understand what you're talking about, right? So second is the standard error. Standard error like that doesn't tell you anything unless you test how many residuals lie in within two standard errors. For this purpose, I told my students you just multiply by 2 over here, and then you, if ABS, you test if the absolute value of this residuals actually lies in within the two standard errors. Freeze it so that you can copy that easily. So now it should be fine. And over here, you can just say sum of all this over the count of all this. It's very obvious now, it's 100% of the points, but this is just in general if you have a longer line, and put it in percentage so that you can, yeah, and then you say 100% of the residuals lie within two standard errors. How beautiful is that? So this is in fact for the goodness of fit. So here, if the goodness of fit is in red, we're just talking about the adjusted R squared. And over here, we're going to talk about standard, the comments about the standard error. Okay? Okay. All right. Let's move on. Let's explain here the Anova table. The Anova table over here, guys, is basically about testing the null hypothesis, again, that all these variables together are useless. So where is the f-test I have? I have the f-test somewhere. I added it somewhere after the R squared and the standard error for you guys. So there's an f-test over here for you guys to take a look at. Okay. It should be somewhere here. Okay. I actually have, okay. It should be somewhere over here. So the null hypothesis here is that the hypothesis of no linear regression, meaning together all the independent variables, this is more for the multiple regression, all the independent variables are not useful or significant in predicting Y. And we want to refute this null hypothesis. Usually in research, a researcher writes his thesis or his research in such a way that he's, let's imagine so that you understand it better and remembers it better. He writes it as if he's saying or she's saying, you know what, I'm going to go with your argument. You know what, there is no linear regression. They're all together, though all these independent variables are no good. and I will show you with my thesis, or I show you with my analysis or with my techniques that this is wrong. So I want to refute it. It's like debate, yeah? Refute the null. I also tell my students with the null hypothesis, null means nothing. What do you want? You want a null bag that has nothing in it? Nobody wants a null bag that has nothing in it. So you always want to attack this, you always want to reject it, you always want to refute it. So you always like to refute the null hypothesis in statistics. And how do you refute the null hypothesis? Straightforward here for the F and for other null hypotheses here on this Excel sheet, we're gonna opt for a threshold of 0.05. So this should be less than. Some like to say less than or equal. I say less than. It should be less than this threshold. So it should be less than 0.05, and I will show you in this Excel sheet why it should be less than 0.05. So if this measure is less than 0.05, and over here, please do not miss the E negative 11. E negative 11 means, for example, if this is 4.4 and it is to E negative 1, this actually, or E negative 2, let's say, this means we have to move to the left 2 digits. So here's 1 digit, here's 2 digits, and this digit, that the next digit we're moving to the left or shifting to the left further, will actually be replaced by 0. So this will be equal to 0.044. How is that so? Because we have E negative 2, which means that we have to move or shift to the left 2 digits or 2 places. 1, 2, and this will be replaced by 0. So it will be equal to I always like to say 0.044. Okay? So 2 digits after the point. So over here, you can say that this is to 11 digits shift and zeros. So this is definitely less. So we can reject, or let me type it better than my handwriting, my horrible handwriting. So basically over here, we say that this is less than 0.05, and this means that we can reject the null hypothesis of non-linearity model, or that all the independent variables, let me just put it as IV, independent variables are useful in predicting the height. We have only one independent variable here, it's age. So now this is the goodness of fit done. This is the significance here of the F test is done. The third one is, after the Anova table is here, is the coefficients. Let's take a look at the coefficients. Usually with the intercept, we don't really mind about the p-value, but which is the significance level. For the independent variables, we really focus on the p-value or the significance level. Over here, the significance level is very, very low. As you can see, it is less than 0.05. This means that this independent variable age is significant. So this is less than 0.05. So variable or age in months is significant variable in predicting height. All right. Now let's talk about interpreting. For interpreting the coefficient, basically, let me walk you through it one by one. There is like a template that they use in books on how to interpret the coefficient. So basically you say, as age increases by 1 unit. So this coefficient basically explains the strength of correlation between this age and or how much this age could predict y, the variation in y. So as age increases by 1 unit, height could increase or decrease. In principle, it increases. Why? Because This is by nature, and also because the sign of the coefficient. You know what? I'm going to write it first in template form, general template. As the independent variable increases by 1 unit, the dependent variable, dv, I'm going to put it dv, could either increase or decrease, right? Depending, of course, on the sign of the coefficient. If the sign of the coefficient is positive, it increases. If the sign of the coefficient is negative, it decreases. This is exactly when I explained the person R correlation. If you guys remember earlier in today's video, I just talked about the R correlation. Where did I talk about it? Here. Remember, I explained to you. So this is why we say when X, or when the independent variable increases, Y increases or Y decreases over here, because we don't usually say when X decreases, because we don't move like this. We usually move from the origin, from the intercept. We usually move from here and shift 1 unit on at a time on the x-axis, as we moving from right to left, if I could say. So we are moving this way. So we are always shifting by 1 unit, increasing by 1 unit on the x-axis or the independent variable. And then we check how the dependent variable responds to that. If the coefficient is negative, the sign of the coefficient is negative, as in the R Pearson correlation, then this means that as you are moving along the x-axis on the independent variable, so as the independent variable increases by 1 unit, what happens here is the dependent variable decreases by the slope, right? By the slope. And over here, the slope is constant on linear regression. So the WY, WX at any point here is the same. It's constant, right? This is for linear regression. Over here, as you are moving 1 unit, so as the independent variable increases by 1 unit, the dependent variable seems to be increasing as well by the value of the coefficient, which over here for simple regression, it is the slope. And the slope is constant, so at any point, it doesn't matter. So for this point, we say as the independent variable increases by 1 unit, the dependent variable could increase, decrease, depending on the sign of the coefficient by the value of the coefficient. Of the independent variable. Okay, so over here, the dependent variable increase or decrease depending on sign of the coefficient. All right. So this is the general template. Now let's use this general template to our example. As age increases by 1 unit, the height increases by, because it is in positive sign, 0.634. Another way that you could write it, as age increases by 1 month, height, average height, we can say it's the mean, guys. Average height increases by 0.64 centimeters, 643 centimeters. Also, if you want to be more, you write it in more natural language, you say as the toddler, as a child, let's say, as the child grows by 1 month, the average height is expected to increase by 0.6443 centimeters. And this is what I really would like you guys to train to write. This is what I would like you to train to write. Yeah, more natural. more natural language, isn't it? So as the child grows by 1 month, the average height is expected to increase by the value of the coefficient. Okay, now let's talk about the last topic for today, I hope, is what happens. A different example is temperature and pressure. Let's take this example, the temperature and the pressure, as you can see here. And let's plot pressure. Pressure is basically changes when as temperature varies. So pressure is on the y-axis, is the dependent variable. Temperature is on the x-axis, is the independent variable. So basically over here we have pressure. I'm gonna do a scatter plot and take a look at the distribution of points. Do you think that these points are actually linear? You could actually draw a linear model here. And take a look here. You could actually add a trend line and specify it as linear and display your equation. And here we go. Here's your linear equation. So basically you could just go ahead and do data and go to data analysis, a regression, and take the y-axis here, and the x-axis is basically this. I'm just making sure that they are correctly and the output, let's keep the output over here for now, or let's put it a little bit over here, and let's take a look. So here is the output. As you can see, this output, let's take a look. First of all, we go over the adjusted R squared. It's high, it's good. And we're going to go over also the standard errors. I already have it here done for you. It's the same as what we've done earlier. We basically take the standard errors, standard error, multiply it by 2, and then do the test over here. And then we found out that all the points lie in within 2 standard errors. So the goodness of fit is not bad. Over here, the F measure, the F test is less than 0.05, so we can reject the null hypothesis. But when we come also here on the p-values, look, it's significant. This is significant values, as you can see over here. It's all significant because this value is less than 0.05. However, when we take a look at the residual plot, there's a problem here. What is the problem? The problem is basically there is a pattern. These residuals are not random. So for this p-value, for these coefficients to be validated, there are certain assumptions you need to test for. There are certain assumptions you need to test for before you actually say that this is what it is, and this is the interpretation of the coefficients of the model. So basically, most of the students just go here, see that this is significant, interpret the coefficients, and that's it. I am done. I can use this model to predict the future values of the dependent variable. And this is unfortunately not precise and not correct. There are certain assumptions that you need to validate. You need to validate the linear regression assumptions before you actually jump into conclusions that this is a good model. First one is the fact that residuals should be normally distributed, but also random. This doesn't look random to me. There is a pattern in here. So when there is a pattern, and this pattern looks like an x squared, yeah? Don't you think so? I think so. Second assumption will be an assumption about the constant variance. This is a very important assumption. It's called, I'm not sure if I'm going to say it correctly or not. I usually say it as heteroscedasticity, but actually I think it is heteroscedasticity. There's a K there that you need to say. So I just know how to say it by saying it heteroscedasticity, but this is the wrong way of saying it. But this is the easiest way to me to say it, which is it's written as heteroscedasticity, but in fact it is pronounced with a K instead of a C here, I think. But in any way, let me just please allow me to just call it or just pronounce it as heteroscedasticity. With a heteroscedasticity, basically you want to just make sure that the outliers in fact has a constant variation, yeah, so, or a constant variable variance. So basically this also means that when you are plotting the dependent variables here, you can see how these the slope here, if we drawing a slope or drawing a better fitted line, a line that is polynomial, because we have just, I'm going to delete this and I'm going to stick to the polynomial or quadratic and display the equation here. Wait a little bit about the equation. I'm gonna comment on it in a bit. We can see that if you draw just the slopes here, which is little intercepts here on each point, you will see that the delta y over delta x is not constant like in the linear regression. So this is another assumption that we need to test for. So basically, to test this assumption, the heteroscedasticity, basically what we need to do is to plot the residuals versus the predicted values. So over here, do I have it done over here? I probably don't have it done. I just checked for normality, and usually we check for normality by checking the skewness and checking the kurtosis. So skewness and kurtosis are easily found functions in Excel, and based on the number of the sample size. Usually the sample size for most research is 100 observations or more, and this is why in general you will find in most resources they tell you the skewness should be in between 0.5 and minus 0.5, around somewhere around here. And the same here for the kurtosis, they use these ranges. However, because I am using smaller sample sizes, I am trying to be very precise. And this is the table that we use when you have different sample sizes with the ranges of kurtosis. This is within a 95% significance level. This is the kurtosis values and the skewness, not values, but ranges, and the skewness range for a normally distributed samples. So basically, when your kurtosis value and your skewness value lies within this range, this is considered to be a normally distributed residuals. So you take the skewness and you take the kurtosis of the residuals and look it up over here. It is very surprising that I got the skewness to be 0.5 for 10. So it lies in within 0.5, lies in within the skewness, and also the kurtosis lies in within the minus 1.7 and 3.48. So if you just do this without investigating and looking at the plot, you will miss on a lot of information. All right, second is we need to plot now the predicted variables or the predicted values versus the in my notes I explain more about the kurtosis and the skewness. Please take a look at them on the notes section if you don't know what the skewness and kurtosis are. And let me just go ahead and start a little bit talking about the heteroscedasticity. And with heteroscedasticity, basically you need to plot the predicted values versus the residuals. Over here, I have in the PowerPoint slides, I have more examples and explanations about it. So please go ahead and take a look at some of these examples. All right, so for now, I'm going to plot the errors. For this purpose, we take the absolute errors. So I'm going to go here, and the residuals here, I'm going to take the absolute residuals. So I'm going to take the ABS of the residual. And then I'm going to plot that, insert, scatter plot. And over here, I'm going to make sure that the x-axis is actually the predicted values. So over here, for the x values, I'm going to put the predicted values. And I really would like to label them and have here predicted pressure. And over here is the absolute errors. All right. And this is over here the heteroscedasticity test. Let's hope that I wrote that correctly. And then over here, we try to find out if we could, in fact, have a significant linear model. So this means that the predicted pressure is, or the absolute errors is actually dependent on the predicted pressure. So over here, we can say that, I'm sorry, something happened. Okay, the R squared here. So over here, I have a very low R squared. So heteroscedasticity or heteroscedasticity is not, there's no evidence of heteroscedasticity, meaning that the values of the errors are not dependent on the predicted pressure, which is the predicted values of the dependent variable, which also means that usually with heteroscedasticity, we are worried when even we plot the y values and the y values look something like that. For example, so as you see the variance here, the variance is very little when the x-axis is little, but the variance increases. What does that mean? For the predicted values that they are away from the line, so this is the line, the predicted values, actual, and the errors here, the absolute errors is actually the distance between the actual and the predicted. This means that the actual values are actually spreading in such a way that looks like a cone, as you can see here. For example, this means that if this is not predicted and errors, this is actually here the independent variable, and this is the dependent variable. And the dependent variable, this is the predicted values, and this is the actual values. This means that the variance among the actual values differs as we are moving or shifting to the right on the x-axis. What does that mean? This means that this model precision in prediction is very high and very good when the independent variable values are low. But as they grow, as they go higher, as the values increase of the independent variable, the model precision decreases because the residuals increases. I'm sorry, this is not, this is, I'm sorry. This is here for this. So this means that when you are plotting, so this is what it means really. So the independent variable, as the independent variable increases and shifting to the right on the x-axis, The values here, the precision decreases because the residuals increase. This means as the predicted values increase, because this is also the linear line, it increases also the same way. As the predicted values increase, the error increases. What does that mean? It tells you there is this kind of line, linear regression. So as this increases, this increases. So if you find out that the predicted values over here and the error, the absolute error term, exhibits such a linear relationship, this is very concerning. This means that heteroscedasticity is actually present, and this means if it is present, if this is found to be true, this invalidates the p-value. This p-value means nothing, and this coefficient interpretation that you spend a lot of time interpreting the coefficient is unnecessary. So this is why I always tell my students, first of all, look at it if it's significant, then start investigating if the error term is normally distributed, and there's no patterns. As you can see in this investigation, this example in particular that I bring to you guys, you can see that it is actually found to be normally distributed. But look at that, lovely people. There is over here, as we can see, there is a pattern. We cannot close our eyes. Where is it? I'm sorry, I just missed it. Where is it? Right there. There is a pattern. Once there is a pattern, that mathematical pattern known to us as x squared here, this means that go back again, you can improve this model by actually adding, and look at that. Even this indicates that the relationship is a quadratic. It's a quadratic relationship, and the variance or the slope here is not constant. So basically, make sure that you fix this. Now, how do we fix this? We take temperature and pressure again, and we add another term. Let me add it here. So basically for temperature, I'm going to add another term, which is basically temperature squared. So I'm going to just square the temperature. This is the easiest way to do it. And I'm going to call it temp x to the power of 2, which is temperature squared. All right, so now let's run linear regression again. So we go to data analysis, regression. Okay, this is the y, and the x is actually now not simple regression, it's multiple. So it's still a linear regression, guys, still a linear regression. You just, let's put it here. It's still a linear regression, guys. It's just that this term, it's an extra term, as if this is one x and this is another x. It's just we added an extra term, all right? So let's take a look. Did the adjusted r squared improved over here? The adjusted r squared was, maybe sheet 2, is it? Oh, here? Yeah. Adjusted r squared was 0.8829. Over here, adjusted r squared is 0.99, so it's really highly improved. Standard error, we have to do the same. I think I already have this is done. So this is the, no, this is, we just did it now, right? Okay, so let's do it together again. So this is what, yeah, this is, I have it over here. So as you can see, guys, this is the same output, and I just had to do the 2 standard errors, and I just tested if this is within the range, and it was, all of them. I looked at then the significance here. It is less than 0.05, so we can reject the null hypothesis, and all these variables are significant within the model. And then we looked at the p-values. P-values here are all below 0.05. And now, for us to validate or interpret these coefficients, before we do that, we need to take a look at the normality assumptions. I took a look at the normality assumptions. They are in within. I look at the plots, and you can see now the plots are different. This is the residual plot for the x. This is the residual plot for the x squared, and none of them exhibit any pattern. Also, looking at the heteroscedasticity, we need to get the absolute errors here and find the heteroscedasticity. That there are other also assumptions, guys. There's another assumptions for autocorrelation, but autocorrelation assumption is necessary for time series values. And there's also multicollinearity. Over here, I expect multicollinearity to be present because this variable is in fact extracted from this variable. So for this investigation, we're just going to take a look at the normality assumption and the heteroscedasticity. So I'm going to just cut these to get them out of the way. And over here, if you remember, the heteroscedasticity is basically by taking the absolute values of the residuals. Oh, sorry, what am I doing? I just want to get it done, right? And then I am going to do the scatter plot. Do not forget to go to the select data, edit, and use the predicted to be the x values. And now you are ready to go. For knowing what you're doing, here is the predicted values or predicted pressure, and over here is the absolute errors. And now let's see if there is a correlation over here or a linear line. So you can see, even if there's a linear line, this linear line does not indicate that the predicted values with the absolute errors are actually increasing as the predicted values shifts to the right. Over here, we find r squared to be 0.3. It's low, so there's no evidence. So this is also expected because as you can see here, in this model, the slope changes. It's not the same slope. So over here, you can expect that the residuals of the predicted values will have a negative sign. Okay, so now let's talk a little bit about something that I've noticed over here. Guys, take a look at this, for example. This is supposed to be 0.0524 x squared. If you get something different, for example, if you get something like 5.2 or 17 point whatever, and it is not exactly the same as the coefficient, just go ahead, select your graph, and go to chart design, select data, and make sure, in this case, just make sure that you actually select the x-axis being this. So you just need to make sure that the x, not the x squared term, is actually plotted on the x-axis. In this case, you will get exactly the same coefficients of the trend line as the output over here. How do we interpret the regression or interpret the coefficients of multiple regression analysis? There are multiple templates. Let's talk about the most common template that we use is as follows. Holding other independent variables constant This is how you start. Holding other independent variables constant, then you start saying, as temperature increases by 1 degree, the air pressure, or the average pressure, is expected to decrease by 1.7, and the units of pressure, so degrees, or yeah, by 1.7 whatever degrees units of pressure. Okay, so holding other IV or independent variables constant is very important to start with when you are interpreting the this kind of polynomial regression analysis. I have another example for you on the I don't have another example, okay, over here, but let me just give you another example very quickly before I let you go, guys. So over here, I'll give you an example of, for example, what if your quadratic formula exhibits something like this, for example, and it's not residuals. This is not residuals. Let's say that this is what this is, for example, going to be something like what? Let me check. Let me just put something hypothetical. Let's say that this is something like 7, for example, minus 0.6 9x plus 0.017 x squared, for example. Let's say that this is look like that. In this case, lovely people, what happens is you just need to visualize, okay? In this case, it's going to be very tricky. You cannot just say, keeping everything constant, the 1 unit increase in x will cause a decrease in y. You cannot just say that. It depends on where you stand on the x-axis. In this case, you just, when you are here at this point, so it seems like the 1 unit increase here in x is actually yielding a decrease in y. However, over here, for example, if you're over here, 1 unit increase in x is actually a 1 unit increase in y. And decrease here is by a certain value, increase here is by another certain value. So writing the interpretation this way, the way that I've just written it for you guys, is not necessarily very valid, really. So this is why in most of the books, they don't even talk about interpretation of the coefficients when we are doing polynomial, or some books call it nonlinear, but I am really conservative. I don't think we should call it nonlinear relationships. We should call it curvature. So this is what we call it, a curvature, a linear curvature, that there's a certain curvature. This could be nonlinear. This is okay, nonlinear, I agree. But whatever we've seen earlier, this one, it could be curvature. So when we're talking about curvature, it's okay. Whatever I just explained to you earlier, how we explain the coefficient could be valid, all right? For the curvature, could be valid. But when we're talking about non-linear, for example, if you have something like this formula, 7 minus 0.069, blah, 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 in this case, interpreting the coefficient is very tricky, and you need to take a look where you stand on the line. As for now, guys, I think this is all what we covered so far in class. This is a very long video. I hope you enjoyed it, you benefited from it, and I wish you a very good day. Good luck. Love you all.